Alright, seems I'm making a video, so we'll do this little preliminary crap and move on to the real show, blah 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 blah, such. Alright, well, I guess that's harmless enough. I can move that back and fine. Okay, looks like I'm here. Shit. Yeah. You people are just taking all the fun out of it, really. Just, being that you're just too belligerently stupid. Alright, so this John Walker character has posted a fairly funny comment. So their physics requires it to take 4 times the fuel to go twice as fast. And so he's found a driving instructor who did a test. I mean, I don't know how good a test it is, frankly, but we'll just say, okay, fine. And his test results are, he didn't even get to 2 to 1. Okay, he didn't even get, like, he had to use twice the fuel to go twice as fast. He couldn't even get those numbers, let alone anywhere close to 4 to 1. And yet he's claiming some kind of victory. And you're just like, you didn't even prove that it takes twice as much fuel to go twice as fast, let alone that it takes 4 times the fuel. So it's so ironically stupid. Alright, so remember, Goofy is always saying that twice as fast doesn't mean 4 times the energy. Yeah, it doesn't mean it takes 4 times the fuel. Well, there's a driving instructor who made a video about accelerating fuel consumption. When he accelerated fast, he is using he's getting 11.8 miles per gallon. So this isn't even true. So these aren't the numbers the guy has on his dashboard, okay? His car is doing the calculating, by the way, which I don't know how much to trust that either. But anyway, the range was between like 23 miles per gallon to 30 miles per gallon in terms of all the wacky ways he could accelerate to 50 miles an hour fast versus slow. 60 miles an hour. 50, yeah. So, I mean, it wasn't even close to being 4 to 1. It wasn't even, like I said, 2 to 1 is in doubt. Okay, so this is just bullshit here. But anyway, it doesn't really matter. He puts down how many seconds it takes, which is completely irrelevant. But anyway, and 19 point something. So he's got 11 and 19. Now, you can understand that, well, sure, it should take twice the fuel to accelerate twice as fast. Their physics says it's 4 times. This number should be 40, whatever, 4. It actually should be 45. And it's 19. So this is how he proves his case. So this is the delusion. They just live in this fake world where they're not even paying attention. They're paying so little attention that he proves the case in the opposite way than his own theory, and is writing it as if he's claiming a victory. That's 1.7 times. Well, it should be fucking twice as much. Actually, the difference between his slow acceleration, his slowest acceleration, and his fastest, the time was actually twice the time. So, I mean, it's, it was obviously a real slow acceleration. I mean, you could argue that, the RPM numbers were 1,500 and 4,500. Huge difference. Okay. So it's not really even a 2 to 1 comparison, and he still didn't get twice the fuel consumption. Okay, more fuel and 1.5 faster acceleration. So again, you expect it to be more fuel to accelerate faster. That's not in doubt. The argument is your theory says it's 4 times as much, not less than 2 times as much. Ugh. So anyway, just so really bad, really stupid, really ignorant, really dumb. So I could play a little bit of the video. It's like I said, it's not that interesting because you are depending on the car. So let's do a run here just to, we won't listen to all of the preliminary hoo-pa, poo-pa. But clearly this guy does not believe it takes 4 times the fuel to go twice as fast. So no chance. All right. You're talking about 9% improvements. We're talking about little tiny improvements here, not big, 4 to 1. No, we're talking about 0.9.
going to be 9% better. That's just the acceleration phase of the journey. You've got acceleration, constant speed, and slowing down. If you accelerate gently in this turbo petrol car, well, I get better economy. If I was to go at a lower top speed...
Right, so these are all, yes, these are things that happen. Okay, this test, again, isn't perfect because he accelerates, but then, I don't really do the test till, there's just a lot of crap in this video. Anyway, so I think you should be able to see all of that. Yeah, so over here, okay, over here is the computer, the car calculating the miles per gallon as an average, So we don't know exactly how many seconds it uses and how exactly it's detecting the fuel and all that kind of stuff. So who knows how useful that is.
And there's 50. Cruise control activated. Be interesting to see what this economy is.
So it starts off at a low number and gets higher and higher as you go further and further down the road because the acceleration is less and less a portion of the average.
Wasn't the best way to accelerate. A lot of interruptions with all those gear changes. Generally, if I want to accelerate quickly, I just put my foot...
So, but you get the idea. It's the best you're going to do is some number in the teens all the way to, say, 30. And it never goes outside of that range ever, and clearly indicating that there's no 4 times here, not even close. Like I said, you could say that twice the fuel, to go 50 miles, to go twice as fast to 50 miles an hour, the argument could be made, this test shows it's not even twice as much fuel. So you don't even use twice as much fuel to go twice as fast, let alone 4 times the fuel. So not even close
down and rev
to validating their moronic theory, and yet he posts a link to this video and comments as if this demonstrates that somehow, it's been demonstrated it takes 4 times more fuel when it's not even close. Alright, so that's enough of that lie stuff. I mean, why bother? These people are just, they're so despicable. Alright, so somebody was saying the Julius Sumner things are worth doing, and I would agree that generally speaking they are. I should have another one here, frankly. Where's the other one? Where'd it go? Damn it. Let's see, maybe I have it over here somewhere. Maybe it's someplace else. Yeah, there's one over here on levers. Let's see what this one is. That one doesn't look good. Yeah. What the hell is that? This is one of those cheap short ones, I think. Yeah, so this is the better. Let's see. We really want to do the Newton ones. I don't want to go looking for them again, but alright. But this one's a good one. Levers and all that kind of crap. So we'll play this one. I think we played it before, but we'll do it again. What the hell? But there's arguments to be made, and I'll make the counter way to explain the phenomenon versus their way, I guess you could say. Alright, so let's see the volume.
It's hard to believe Mint's new family plan is just $15 a month per person.
Yeah,
so
whatever.
I've asked my wife.
Yeah, fuck you. Okay, that's okay. Probably could do a little tiny bit more.
How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and...
Yeah, the quality of the video sucks. Let's see, maybe YouTube is cheating me. 480. Let's see if I have any better choices. No, that's the best you can do. Doesn't look like 480.
Physics is my business, and our very special business today is the subject of simple machines. Simple machines. Now, when you study these matters in school...
Well, that's not what you called the title. Somebody else titled your video inappropriately. Yeah.
It is usually said that these are the 6 simple machines. The lever...
So that's the big one, right? And then the inclined plane is the second one. And you could say, well, that's, it's a stick. Yes, it's close to a lever. Anyway.
Or as some pronounce it, the lever, the inclined plane, the wheel and axle, the screw, the wedge, and the pulley. And I wish in this program...
Didn't say gear, which is, right? Gear would be a good one. I mean, gears are not exactly any one of those things.
...to show that really all of these reduce to only two, the lever and the inclined plane, and what is better for us...
Sort of hard to see the tire on the road or a wheel on a road as a lever, but I guess you can do that, you know, or it's a, you know, well, it's not a very good inclined plane, frankly, so yeah, it'd have to be a lever.
...to contemplate is the following, that all of the things I will have to deal with here today are the most plebeian and simple and homely and commonplace. And my purpose is essentially...
Too bad your purpose wasn't to just see if it takes 4 times the fuel to go twice as fast, and then you could get rid of that whole... You could destroy particle physics, because, you know, particle physics is founded on that crap.
...this, that when you pick up your fork and knife to eat your dinner, I hope you would recognize that you are using some levers. Indeed, the sharpened blade of the knife is an inclined plane in addition to the tool itself being a lever or lever.
And it has gears on it, too. Anyway, so yeah, I just don't, you know, you can only push these analogies so far, and that's, you know, I think that's pushing it.
And how about the prongs of the fork? The prongs of the fork are usually sharpened a little bit, so they are wedges.
Oh, well, we know that's not really that important, so we know we don't need the wedge. So that's sort of bullshit, right? Yeah, that's bullshit. It really isn't a lever or an inclined plane, okay? It's a what do you call it? It's not a projectile, but it's a, you know, it's a higher, it's a more concentrated pressure. You're just saying I'm going to increase the pounds per square inch by changing the surface area that I'm poking the force in with. So it's a, you know, you've done a increase the pressure by decreasing the surface area thing. So that's another, I mean, it's hard to call it a tool, but that's another method of making a tool.
And wedges are inclined planes. So let us go at random to some of the things we have here, and you will see exactly what I mean.
Well, there's no point in me saying it, because you already used 2 examples that were kind of lame, okay? I don't need a sharp knife, and I don't need a pointy fork. So the inclined plane doesn't have a damn thing to do with it. So that's sort of bullshit, right? So that this is really just an argument. You should be arguing about how you can increase and decrease the amount of pressure applied by decreasing the surface with which you apply the pressure, which is in a way of increasing the velocity, you could argue. You're increasing the velocity of the impact by spreading it over a smaller and smaller surface area.
Consider, for example, the following. Here is a block of wood in which I have already lodged some bolts and screws and other things.
Yeah, did you do that when you were like 40? Yeah, I don't put them all the way in, though, because I want to save for some of the fun for later. So, you know, I didn't put them all the way in. You know, it's so much fun.
Here is a screw, and I'm going to attempt to lodge it further into the wood.
With the crappiest screwdriver within 3 miles, right? So they looked around and says, can we find the crappiest screwdriver that exists?
With a tiny screwdriver.
Okay, you did it on
tiny
purpose.
Screwdriver. No success.
Yes.
Why?
Why? Because the handle is really small. So yes, you'd have poor leverage on your handle. Okay. So if you make it a fatter handle, then you'll have a lot more luck.
Well, let us look at what really happens. The handle of the screwdriver I have enlarged, looks like that, and I apply a force this way and a force that way, so that I turn it about a central axis, and these 2 forces...
So this is the leverage thing, just in the sense that you've taken the straight, you could just straighten all this out into a lever and just make the argument that you're increasing and decreasing. So you're essentially concentrating the force again by changing the surface area over which it takes place. So, but it's definitely got the lever written all over it. The, you know.
equal and oppositely directed and parallel are said to be a couple. C-O-U-P-L-E. You see a couple.
Well, there we go. We had that couple word in one of the other guy's 1918 whatever book. So yes, the old folks use this word coupling.
Couple of forces acting in this way.
Oh, a couple of forces is what it means. Isn't that cute? No, not really.
Now, the small screwdriver had too small a radius. So what do? I use a big screwdriver, and the same force will accomplish my purpose very readily, as you will see. Here is a big one. And the handle, of course, is very much bigger, so that the torque, or the turning effect of my force...
So it's just like the gear argument. You have a big gear on the outside and a little gear on the inside, and what you're basically doing is allowing you to turn the outside in a faster motion, technically, and create a slower motion on the inside that's at a higher pressure.
Is very much increased. There it is. Beautifully accomplished.
Yeah, he probably used two hands and we didn't see that. So we couldn't even get two hands on the little screwdriver. It's kind of funny. Kind of funny.
Consider now, I remark that a threaded cylinder, which we call a screw, is really an inclined plane. And I hope you see the inclined planeness in this threaded shaft. I'm going to prove to you that it's an inclined plane.
Yeah, so what? I don't know if it still requires an awful lot of other circumstances, like the whole circularity of it. So,
here I have an inclined plane cut out of paper, and it goes uphill to my left. I'm going to wrap this around a cylinder, and I hope you see that what I will get out of it is this. Here is the cylinder, and I wrap the inclined plane around, and I get a threaded shaft, which is a screw. Now watch this.
Yes, I mean, we could all see that, but whatever, okay.
Here, I'm going to wrap it around. Let me finish it here first, and there you will see the inclined threads. Now, I have wrapped this one around so that the threads go like that, which is a left-handed screw. I have cut the other one so that when I wrap it around, it gives me, I hope... Yes, let me turn it over. No, there.
Yeah,
notice I'm a little twisted up here. Well, notice I'm glad I'm twisted up because this suggests that...
It suggests that you drink a little too much. Oh, fuck. It's a little funny. I mean, it's only a 15-minute show. You're really just like, oh, come on. Can't we get this straight?
Even professors of physics can get a little bewildered. I know where I made the mistake.
Yes, you put it upside down.
One of these I have to turn over and use the mirror image, and then it will give me a right-handed screw. Now, this business of left-handed thread and right-handed thread, very important. Illustration. Oxygen tanks used to take care of sick people are right-handed threaded. Nitrogen tanks, on the other hand, I believe, are left-handed threaded, for the very reason...
So he believes it, but I don't know. Yeah, but yes, it would make sense not to connect the nitrogen to the oxygen, so yes, makes sense.
That then nitrogen could not be inadvertently and accidentally fed to a patient who should be getting oxygen. See, very important idea. Let's look at another one. Here is a bottle with a screw cap, and the housewife finds that she cannot undo it because it is too firmly fixed. What does she do? Answer.
Meditates. You know, and then like there's some yoga and such, and then all of a sudden just does that superwoman thing. And it all works out okay. I actually tried that opening a bottle once. You know, I just said, okay, meditate. And now, you know, give it your best effort. You know, concentrate on a best effort. It did seem to work.
Provide herself with a lever and a notched jaw, which is essentially an inclined plane. And then she puts it on there, and ever so...
Well, the screw that you turned was supposed to be an inclined plane, too. So it's an inclined plane with more inclined planes, blah, blah, blah. And obviously it's not the inclined plane part that's doing the gripping, it's the little pointy stuff that sticks into it and cuts right into the metal. So it's not really the inclined plane, it's just pointy things. But okay, whatever. Again, it's that reduction of surface area to increase pressure. That's what enables it to bite.
Gently. There it is. So I say that for little bottles with small screw caps, you have a small Stilson wrench, and for medium bottles, a bigger Stilson wrench, and for very big bottles, a very big Stilson wrench. And any well-equipped household, I think, should have...
Yes, just that stuff should be hanging on the kitchen wall. Yep.
At least 3 Stilson wrenches. Consider.
I probably have about 14, but, you know, it's not like hammers. You know, I have 36 hammers, but, yeah, you know, wrenches, not so much.
For the housewives and the boys and girls and the teachers, here is a great...
Actually, I have a monstrous one, which you're almost saying, who the fuck would ever use this thing? It must weigh 20 or 30 pounds, and, you know, it's 4 feet long. And I've never had occasion to use it. Yeah.
Now, what is a grater? A grater, well, a grater, you grate with a grater. There it is. And I say a grater is an inclined plane. Very...
I say it's pointy again. So, again, it's, you know, the inclined part is sort of unnecessary as long as you have the pointy part. So, if you could make it thin enough, you know, razor blades or something, you know, it's a little tiny point. So even if you dull the razor blade, it would rip through a piece of cheese pretty easy. So again, it's more about the only reason why the inclined plane has any utility is because it starts with very high pressure at the pointy bit. So it's really the wrong way to explain the advantage of the inclined plane as a... Why can't I think of what would you call an arrowhead? I mean, a pointed... You know, I know there's got to be a more sensible word than the nothing I'm coming up with. But anyway, doesn't matter.
Clearly an
Probably doesn't matter.
inclined plane. How about a wedge? A wedge. A wedge is clearly an inclined plane. Consider the following. Here is a railroad spike. Indeed, it is pointed. Quite like nails are pointed. Why? They are inclined planes, and the advance into the railroad tie is more easily accomplished because this is an inclined plane.
It looks rather short, frankly. It's got to be for like a really small train.
Let's go to an ordinary hammer. Here is a nail that I've lodged in here. A lot to say about this. Let me use the hammer as a lever. Not much success. I improve its mechanical advantage by providing a block under the head, and there. And now what must I say? What must I say? Very important.
It's very important that you know when you pull the nail out, it got hot. Ooh.
Do I feel when I feel this nail? Very hot. Friction develops heat, and friction is...
So again, and friction is the loss of energy by connecting things together. So again, you're doing that coupling thing. You're touching things against each other, and the friction, okay, is you losing energy to the other object. So
a dissipative force, always arising when work is done.
So it doesn't always have to arise. So that's the part I really hate when they say that. You don't always have to produce heat. You can create systems that are, you know, perfect or whatever, and don't waste any of the energy. So you want to do a conversion from this to this, you know, and the idea is if you do it, you can end up losing through heat. You know, the turning, you know, could cost you. And there are ways to do it, though, that are more efficient and don't involve changing any of the energy into other directions. So I guess that's the way I describe it, is when you're using energy, you have everything moving in the same direction. All the fish are going the same way. And when you're losing it through heat, it means that fish are going in the wrong directions. So you're scattering your energy. So the less scatter you have, the more efficient your transfer of the energy. And the more scatter you have, the more heat. But it's not a necessary condition. I mean, clearly superconductors prove it's not a necessary condition.
And about which we spend fortunes to eliminate. Very important. But remember, if we could accomplish the elimination of friction, no motion whatsoever would be possible. A very terrible thing to accomplish.
No, that's not true either. So, again, it's a, but whatever. I mean, in what context is that statement made? So, it just doesn't mean much, because you're saying that, yes, for two things to exchange, they don't need a third thing to, mitigate the exchange. Two things hit each other head on. There's no need for friction.
Contemplate. Here I have another one in front of me. How about a nutcracker, a lever? What happens? I put the nut in here, and then easily accomplished, effortlessly.
Well, you should have put it further in and shown how it doesn't help at all. So if he puts the nut all the way at the end, it really doesn't do you any good at all. And you need to put it closer and closer to the fulcrum to concentrate the pressure.
Here's one for the housewives and the boys and girls and the mothers and fathers and the school teachers.
Oh, please. And the janitors, apparently.
A broom. A broom, I regret to say, is a lever. And next time you sweep the house, I wish you would have some regard for Archimedes of the 3rd century BC. And I'm going to show you how the lever can be used in an enchanting way. The usual way is what? We hold it there and push here, push here, push here. The fulcrum here and the force there and the load down there. It can be used in another way. Watch me. I'm going to have the fulcrum here and I'm going to push it here. Not too
so this is how to sweep the floor for retards. I mean, it actually is for the retards, just to show the retards how they can stay good and retarded. You want to keep proving you're retarded? This is what you do.
Handsome way to use a broom, but it can be used as another class lever. More on the same.
You can hit criminals with it too. So hang that on your wall.
If indeed the subject is getting, let us say, monotonous, it should not be. All these things are levers. Here is a piece of metal. Here a little pair of metal clippers. I have difficulty. Why? Not enough lever arm. Not enough lever arm. A larger shears, effortlessly. There it is, like cutting butter. Or consider a file. What is a file? A file is a succession of inclined planes.
Well, they're wedges, so they're double inclined planes. Whatever. But obviously, that's the pointy bit again, the little pointy bit.
And regarding a file, I hope sometime you will be able to go to Milan, Italy. And in the Museum de Leonardo da Vinci, there are many of Leonardo's devices, and one of them is his file maker. And when I was there last, I used it and made, indeed, some scratches on a file. How about a meat grinder? Oh, nobody uses a meat grinder much these days because it's done for you.
It's kind of a disgusting image, but whatever.
But if you will look inside...
Everything can be perverted. It's just so easy to pervert things.
If you will look inside, you will see that that is an inclined plane. Beautiful there. The camera catches it nicely. Here it is. Here's one of the cutting tools from inside, and you see it is an inclined plane. How about an egg beater? An egg beater. An egg beater is not a simple machine. An egg beater is a compound machine made up of a lever,
Ears.
the handle, and some geared wheels. And what do? We turn the geared wheel. There is a certain number of notches on the big wheel and a certain number there.
And that ratio would be the same as the ratio on the lever of the distance from the fulcrum, so you could just count the little notches as inches, and so you're converting whatever 10 to 1 kind of difference, 15 to 1. So if you convert it to velocities or something, it would be you're turning on one place, you're moving at a velocity that's 15 times faster than the other thing turns at.
The handle is so long, and so we speak of the mechanical advantage of...
Yeah, so it's essentially 2 levers, because you got this, the handle is doubling the size of this gear, and then that gear is 15 times bigger than the little gears it's going to turn.
A simple machine. Meaning what? How many times is the force multiplied when we apply a force? If, for example, with a...
So we're not multiplying the force. The force is always the same thing. It's a certain amount of stuff that can be distributed over a certain amount of time. So it's always, you're not changing the force. You're converting what the force is made out of in terms of its mass and velocity ratio, or its torque. So that's a distinction that should be made. The force isn't what changes. It's how you apply the force is what you're changing. So you put a pointy arrowhead on the arrow, you're not changing how much force the arrow's applying, you're just changing how much pressure per moment of time it's going to be able to apply to the surface. So the atoms it does hit, the small number of atoms it does hit, it hits with a high velocity.
Force of 1 pound I can lift a ton, then the mechanical advantage is 2,000. Let me go further. Here is an interesting thing. Pulleys. Pulleys. Now it is very important that I say something about pulleys. When students and boys and girls study pulleys, it is usually said that to find the mechanical advantage of a pulley system, you count the number of ropes supporting the load. Now, I should say that this is not a good thing to do. It sometimes leads to the right answer, but often the right answer is gotten by physically wrong means. And this is a very important philosophy to remember.
Yeah, don't get the right answer. Shit. Bad idea. No, that's a good idea.
Getting the right answer is the least important of your endeavors. What must be right is the logical, analytical reasoning that leads to it. So I would urge you to study...
No, go study pulleys. He's not going to give us the answer, so he's just going to tell us we should go study it.
Study pulleys and learn how to find the mechanical advantage without counting the number of ropes. Here is a pulley system made up of 2 blocks with 3 sheaves each, or 3 pulleys each, rather, and I can lift an enormous force by the application of a small one. Notice, friction is not playing an adequate role, and so the system unwinds. And when I talk about pulleys, what name in history must come to my mind?
Pullacles.
Answer, Archimedes. Because you remember he designed all kinds of machines of war in order to protect the city of Syracuse against the invasion by the Romans. And I would urge you to read the story of this great adventure as recorded by Plutarch. The siege of
Plutarch.
Syracuse by Marcellus, the Roman general. Where am I now? Where am I?
Yeah, you really did lose track. You're really just rambling through the woods.
Let us take some ordinary cutting pliers. What
You already did this, really, frankly. I mean, the snips were the same thing. Come on.
is a cutting plier? Well, we say it in the plural, pliers. Wire cutters. First, it's a lever. Secondly, it's an inclined plane because the cutting jaws are inclined for sharpness. And
Yes, so sharpness should be the word you're using.
so effortlessly, I cut a wire. And so, ladies and gentlemen,
Wow, they did a cut. Amazing. So they could actually edit, and they never edited any of his shows, but this is the first time I saw I edit one of his shows. So it's kind of funny.
And boys and girls, we come to the end of this program, indeed to the end of this 15th program, and what has been my singular ambition throughout the series.
So I guess they were running out of subjects. Yeah, I don't know, maybe he only made 15. Well, it says 17, 16. Well, you got a chalkboard 16, so maybe we'll have to watch that just for fun.
It has been just this: not to teach you any physics, not to assign any
Well, shit. Then what are you doing?
lessons or any problems, but rather to point up the beauty and the drama in all of this. And
Oh, fuck. Yeah. Who wants beauty? I don't want any of that crap in my physics. I want you to understand how the mechanical universe works, period. That's it. You want the instruction manual. Fuck this drama and beauty crap.
to excite your enthusiasm and your curiosity, for these are the foundations which will lead to your better understanding. Now, what have we done? What do physicists do? What is physics? What is science? That's an all-embracive term. Science, of course, is what science...
God, I only have 43 seconds left. Oh, shit, I should have started that subject some other time.
Scientists do. Physics is what physicists do. And what do physicists do?
Talk shit, mostly, apparently. They're really good shit talkers. No, I mean, they're not even good at it. That's the whole point. They're pretty bad at it. They tell you stuff is true. There's no evidence it's true. They just make it up, and then they tell you for forever it's going to be true because we said it was true once.
Physicists explore how nature behaves, and I urge you to spell that nature with a capital N. So as you go about your daily affairs, your school days, your days at home, your playing hours,
It is an N word, frankly. It's in the right category.
I would urge you to have a regard for the things all around you, for they are filled with beauty and drama.
I don't know why that's, again, why would I be a whore for that if I'm supposed to be smart?
And seeing how nature behaves will give you a full life. And I thank you for listening.
Whatever. Says the kook. So anyway, it's funny. All right. So I don't know. They say this is lesson 16, but it looks like it was much better produced. Ideas of heat. Yeah, so this is probably not what I'm looking for. I really should go back to the Newton ones. But he does have a chalkboard. I mean, that's a huge difference.
Could I get the 10-piece chicken McNuggets? Wait, no, Big Mac.
Fuck you. Fuck you. Fuck you. Fuck you. Fuck you.
Sir?
Fuck you.
I'm still here.
Fuck you.
Get one favorite like a Big Mac or 10-piece chicken McNuggets and get another for just $1 right now at McDonald's.
Fuck you. Fuck you.
Teeth were made
Fuck
to
you.
indulge.
Oh, gross. Fuck.
The new Colgate Optic White Comfort Fit LED.
Alright, 14 minutes, yeah. Weird. Okay, enough of an intro, thank you. That's the PBS logo on it. It's funny, so I'm like this was made by Australia and PBS.
How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is...
Oh, and it's a new season. They gave me a new shirt, but I mean, this table sucks, and it's not, I don't know, and I still have my, colored paper to draw on, but they gave me this blackboard, and I don't know, I'm scared.
the subject of heat and temperature. Now, to refresh your mind on my philosophy, as in the first series, which we did on mechanics, I must say the following.
Those bastards made me do all kinds of stupid things. Yes, I wasn't trying to be stupid. They made me be stupid. So we're not going to do any of that anymore.
This is not a lecture in physics. I propose rather to show an array of demonstrations, dramatic and exciting, in the subject before us, with the purpose for the...
Well, and I will explain the ones I understand, and I will pose it as a question. All the stuff I can't figure out, I'll just pose it as a question.
The purpose of stirring your curiosity, arousing your enthusiasm, pointing up the beauty and drama of these things, so that each one of
More of this beauty drama thing. You just don't, don't really get it. Let's see. Let's see if we have any comments. Save the day or something. Let's see. This is pretty interesting video showing different kinds of levers. Okay, indeed. This guy won a prize and got to visit Einstein in person. He was obsessed with Einstein. So is Merker. Yeah, that's you. You're seem to be obsessed. I mean, obviously Einstein, I would argue, Einstein did some good physics when he was young, okay? I mean, the whole Brownian motion thing, the whole photon, photoelectric effect, those were good papers. But the relativity crap, it's just crap. It doesn't work. I mean, there's no equivalency principle. I mean, if you use it as a principle, you could say, yeah, there's a certain kind of equivalency in motions, but to say gravity is the same as a punch in the face is just kind of missing the point. Damn, the video falls short at the end of it. It doesn't have much of a punchline, that's for sure. It wasn't much of a punchline video. Alright, well, we'll play this even though heat and temperature isn't very interesting.
of these demonstrations will invite you irresistibly to go and do it yourself with your teachers, to see the beauty and the excitement that can be uncovered in these things.
Whatever.
So, this is not strictly a lesson in physics, but rather a lesson in the excitement and drama in the subject of heat and temperature. Now, I would remind you, heat and temperature.
All right. And what I would do if I was teaching, okay, I would explain that all it really is, all heat and temperature really is you taking energy in a direction and scattering it in different directions. You're just making little atoms move, and every time the atoms move, you have to use the energy you had, the fish you had. So it's all like fish swimming, and if they stay in a school, you're conserving your energy, you're not losing it to friction or heat. If they start swimming in all kinds of directions, then you're losing what kind of force you can apply in the direction you were going, because it's all going in all these scattered directions.
For this and subsequent lessons, it is absolutely essential that the difference in these words be understood. And for this purpose, now, some demonstrations. Consider first the following. I have here a glass tube in which I have put a little mercury, and on top of the glass tube...
Kind of hard to sit there and change heat into something other than temperature, so I don't know how exactly you say these are different things. It's, you just have an index. No motion, a lot of motion. That's all there really is. So temperature is just measuring the motion in atoms.
Some little bits of chipped glass. Little bits of chipped glass. Then I have drawn the tube down by heating the glass, pumped out some of the air, and then sealed it off. So we have here a tube with some mercury and some little glass and largely empty space in here. Now what am I going to do? I am going to heat this
I don't remember this video, so yeah, this must be a season I didn't see where he had the chalkboard, so I'll have to watch these videos. So I wish they would put these in rational places where you could, I wish they were all in one place.
This tube, heat it. This will be my symbol for adding heat to a system, much like a candle. And I have a warm feeling for candles because my...
He has a warm feeling. Oh, he was molested, by a candle. Yes, that's a real complex symbol he uses. So he has the, whatever. What else could that be, right? A little thingy here. It could be, I don't know what else that could be.
Beloved friend Michael Faraday gave 6 one-hour lectures at the Royal Institution on a candle. And about Faraday, I will one day speak when I do some programs on electricity and magnetism. So I'm going to heat this. And what?
Yeah, I tried reading Faraday's book, and it was just, on and it really, I mean, you really can't you can't do 7 lectures on candles.
Will we see? We will see after a time the little bits of glass dancing about very energetically. So I am telling you that heat is a mode of motion. Let us do that. Here is the burner, and I am doing this with some caution because we could explode the thing and have some disaster. Now I am heating it.
Yeah, big disaster. Mercury vapor. He's not wearing glasses, right? I mean, just, breaking the rules here a bit. Bad lesson taught.
I am heating it. I am heating it.
It's not really working.
I am heating it.
It's a complete
Wait a minute,
failure.
I think I'll take another one. I see a little soot on the bottom of that other one, which may interfere with our operations.
I
am heating it.
Turn the flame
I
on.
am adding heat energy to it. There we are.
Oh, there we are. Okay.
Look at that agitation.
There we go.
Heat is a mode of motion. Heat energy.
So, he's not going to explain, though. It's the mercury's vaporizing, and the, mercury vapor is what's pushing up on the glass pieces, so.
I have communicated thermal energy to the system. Now, who was the first one to tell us, to suggest that heat is a mode of motion? I am led irresistibly
to Newton. Let's hope. Yeah, it's probably before Newton.
To show you a picture of one of those
Benjamin Franklin.
rascals known as the Bernoullis.
Oh, okay, the Bernoullis. He loves the Bernoullis.
And I have to see. That's the camera. That's the camera I'm playing to. This is one of the Bernoullis. And you may remember on my programs on mechanics, I made reference to the Bernoullis and did a program on Bernoulli.
Yes, and all of them were geniuses, except for the girls.
They were a family of over 100, all geniuses, not one an ordinary man. Now more.
The girls were all flushed down the outhouse. There's no, not one an ordinary man. I mean.
Regarding heat and temperature, let's get over here and consider the following. Here I have 2 beakers. This beaker has a little water in it, and this beaker has much water in it. Now, I tell you that if I put thermometers in these, that they read the same. Therefore, I tell you that they are at the same temperature. Same temperature. But is there not much more stuff here in a state of agitation than in here? Accordingly, they do not have, let me write that, unequal heat. Same temperature, but different amounts of heat. Now let's look at another pair.
So that's the distinction it's making, that heat is something to do with density. So how much material you have that is at a temperature is heat. And I don't know if you need to make that distinction. I mean, I think heat is just the quality of having temperature. It's not the quality of having, it's not a volume of temperature.
2 beakers, one with a little water, one with much water. I assert that if I put the thermometers here and wait for the time to elapse to get a proper reading, I tell you that
the little one will cool faster than the other one.
These are vastly different in temperature. This little one has a high temperature, and this one has a low temperature. And what am I prepared to tell you regarding these? From what I have said, heat is a mode of motion. There is much more stuff in motion here than here, but here, the temperature being higher, the motion is much faster. So I could say that...
Well, he's sure not making much sense. Yeah, so it doesn't make any sense to me. The temperature's the same, the motion's the same. You're just talking about there's more volume of atoms moving in the big beaker. But if the temperature's the same, the amount of motion's the same. I don't know what he's saying.
These have the same heat energy. The same heat energy. I hope you are getting the idea of the distinction between heat and temperature.
No, you really made a mess out of that, frankly. Big, sloppy, stinking mess. Yeah.
Let me try it another way.
Yeah, please. Do it some other way.
Consider the following. Consider this. I have here...
Some of these videos are clunkers. I mean, some of them are really, he goes through a lot of things really quickly, lots of things you didn't think about, blah, blah, blah. Good. But some of these are just, oof, eek.
Some spheres of different materials. Brass, lead, aluminum, iron, and so on. Now, this experiment that I'm going to do, I call virtual. Virtual. As distinguished from some demonstrations
real.
which I do,
Yeah.
which we call real.
Oh, yeah.
Real
Fake.
ones are those I really do, and virtual
Fake ones
are ones we will have to imagine.
Yes.
Now, I have often said that imagination is a very necessary ingredient of your life and work. So you will imagine that...
But it has to be disciplined by some references to reality.
I have put these spheres into a beaker, and I have added some water, and I have put it on a tripod, and I have put some heat energy under it. Here it is. There is the beaker. There are the spheres in there. There's some water in there, and I apply some heat energy. And I cook them, as I would say, for a long time. Long time I cook them. Boil the water and boil the water.
They all reach the same temperature, okay, because the heat is going through the glass and it's into the water, so the water is going to heat the metal pieces, and the metal pieces are going to be at the same temperature as the boiling water.
Will you not agree that after a time they will all be at the same temperature? The same temperature. Now what do I propose to do? I propose to take them out of the beaker with a forceps and put them one by one on a block of paraffin. And what will we observe? An astonishing thing.
There we go.
We will observe that they...
So it really wasn't a virtual experiment. He did it, and he's just showing us the outcome. So, nothing surprising there. So the more dense the material, the more obviously atoms moving. That means there's more capacity for movement to be passed on because it's a greater mass. So you could say it has more momentum. Okay, so you just convert the heat into understanding. You have two elements that make the heat. The volume of the stuff heated, okay, and how hot is it. So it's just mass and velocity again. So the higher density, more mass, okay, more energy stored in the more mass. So even though they all had the same temperature, this one has more to give than this one because it has a greater density of mass.
Sink to different depths in the paraffin, meaning, of course, that they possessed different amounts of heat energy.
And they also weighed a different amount, which is part of why they sink into the wax, is you got to put in the gravity part. So there's a little cheat built in that, yes, the heavier material will sink further into the wax than the lighter material. So it's not a very good experiment, frankly. Not a very good way of extracting the one fact you want to extract. You'd be better off putting them each in a beaker of the same amount of water and see how hot they make the water. So obviously the more dense one would heat the water more than the less dense one, and that would be a better experiment. I just thought of it off the top of my head, so that's what he should have done. Because using gravity is not a good idea.
Different amounts of heat energy, different thermal energy, different heat energy. Why? They were able to do different amounts of work. Consider the same thing viewed another way. These
You could just think of it as a spring and storage of energy. How much energy can it store? What's its capacity? So the more matter it has, the more capacity it has.
spheres are all steel. I heated them to the same temperature in such a beaker of water. And what do we discover? That even though they are at the same temperature, they have melted different amounts of paraffin.
Right, and that's not a good example either because of the whole round problem. So they're not sinking beyond being halfway in. So now you have the roundness advantage, which is the smaller your diameter, the faster you'll push through the frickin' wax.
And therefore we're able to do different amounts of work. I hope you see, boys.
So what you should see, boys and girls, is there's lots of experiments you could do, and you do them, where you've, taken and thought them through and engineered the experiment to actually isolate the variable you're trying to measure. And then you can do experiments where you have a whole bunch of other variables fucking with your ability to isolate the one variable you want to isolate. And that's what you should learn, boys and girls, is you can do experiments very well, or you can do experiments that are pretty shabby and stupid.
Girls and ladies and gentlemen, that I have been using the words heat and energy synonymously because they are one and the same thing. Heat is a form of energy. Now I have suggested...
Heat is made out of the same stuff all energy is made out of. It's movement, it's mass moving. So yes, heat is the same as weight, is the same as pressure. It's all made out of the same thing. It's just an example of matter moving.
Same temperature, different heat. Consider a plebeian little adventure. Here I have 2 potatoes. An enormously large one and a small one. Let us put them in the oven and bake them. You will agree that after some proper elapse of time, they are at what? They are at the same temperature. But now you know that this one has vastly more heat energy in it than this one. Same temperature, different heat energy. Or consider another. We wish to show again that heat is a mode of motion. I have here 2 beakers. This one, I say, has cold water in it, so I report to you. And this one has hot water in it, so I report. Now, mark you, I said that this is cold and that's hot, and I reported to you with my hands. That is a very unreliable report, as I shall show you in a subsequent demonstration. But what do I want to do here? I am going to drop a little food coloring in this one, and we will see the rate at which it diffuses.
So that's a good experiment. That's interesting because it basically will show you that this water has a bunch of activity in it and this one doesn't have so much activity. And so that's a good physical example.
Then I'm going to drop a little food coloring in this one, and we will see the rate at which it diffuses there. Here we agree. Same amounts of water, very nearly. Oh, I stole a little, so I'll put it back. There we are. Since we want to do the experiment with some reliability and integrity.
Yeah, that makes it integrity. This is always a good way to show your integrity.
We will see the diffusion here, I hope, much more rapid than in the cold.
I
Watch
guess
it.
you choose the eyedropper, frankly. You're really pushing your luck here. So, yeah, see, I mean, drip, 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 drip. So that's already screwed the experiment. You should have just used one drip.
There
Drip,
you
drip,
see
drip,
it
drip,
going
drip, drip,
down
drip.
so fast. I think it's going faster in this one. I do think it's going faster.
So he talks about integrity and then does something this bad. I think, yeah. Well, yeah, you put it in later and it's further down, so yeah, it's going faster, but really the way you dripped it in could have a lot to do with that. You didn't do that in a standard way. No quick release involved here.
And hence I have shown you that there is much more.
Why would he do this experiment? Actually, it's really not showing you much accelerated dispersion. I mean, this doesn't seem all that much more diffused. It didn't take over the beaker, all that quickly.
Agitation in the water here than in there. To sum it up,
To sum it up, that's pretty shitty, because that almost looks like, that's pretty close to the same, not much difference, blah, blah, blah. It's really kind of a shit experiment.
a simpler phrase. What we mean by the temperature of a system is this. What is the average kinetic energy?
Wrong word to use. So obviously it means kinetic energy in the not potential energy way, not the kinetic energy formula way.
Of the little elemental parts. The average kinetic energy, 1/2 mv square, and I put a bar over the V to mean average. What is the average?
Yeah, whatever. Obviously, you don't need the 1/2 and you don't need the square, and you just have to say what's the average mass, what velocity is the average mass moving, and how many are there moving.
Kinetic energy. Now, if we take all the kinetic energies of the little particles that are in motion and sum them up, that's the Greek letter sigma, which you will encounter when you study the calculus, which means you add up all the 1/2 mv squares, and you get the amount of energy in the system.
So, you just add up the MVs. You don't need the MV squares. But whatever.
Consider another. Look at this. Very dramatic as a virtual demonstration. Here I have a beaker of ice. If I put a thermometer in that beaker of ice, you know that after a time, the thermometer will read 0 degrees centigrade. The ice is not super cooled. Accordingly, the thermal energy in the system is so much.
So it's, again, not a very good experiment because he's really measuring the temperature of the liquid water, so it's not going to quite be 0.
The temperature is so much. Now let me apply some heat under here. Add some thermal energy. I am adding heat energy to the system. We see some of the ice melt, but a most remarkable thing is witnessed. Namely what? That there is no change in the temperature. So we have had change of state, but no change in temperature. And about this I shall speak on another program. Coming back to the unreliability.
Depends on what you're measuring the temperature of. So I guess you could say if you measure the temperature of the air, it'd be getting warmer. If you measure, obviously the ice is frozen, so it stays its temperature, and the water is going to stay its temperature.
3 beakers. Cold, medium, hot. I put my hand so. This one feels cold, that one feels hot. I put them here, and I cannot tell you which is which. Suggesting what? That the physiological determination of heat and temperature is most unreliable.
Relative. And
So, I thank you for listening to this adventure, and we shall return another day.
so he returns with the same subject. So I guess I have to go to the channel, and we'll see what he has here. All right, videos. All right, 21, 29, 26, 19, 17, 16, 20. Okay, so these are... I've only seen the ones with the up to 15, I guess. So let's see if they're all here. I'm going to get to the Newton ones. 40... See, here's 39. He's back to the stupid... He's got rid of his blackboard. So I have seen these. So he had the blackboard and they thought it was a bad idea. I don't know. It's kind of funny, right? They got rid of actually a good feature and went backward to the old style. I don't know. Don't know. Hard to tell, frankly. They're all so inconsistent. It is really interesting that they're all so inconsistent. So do we do the first law? Well, anyway, I'm getting, yeah, I'm getting sick of it. Let's see if there's any comments to deal with. That might be more interesting. Well, I shouldn't have said that. That's too hopeful. Nope. Okay. Nice. The importance of a quick release. Yes. Okay. So, not much action in the comment section. So let's just see where we are. 15 viewers. Yeah, you should be doing a little better than this. All right. So, I guess I'll see if I can... Where did I do with that channel? Here it is. Alright, well, let's do the Newton first law one again. And, yeah, lesson 2. Okay.
I am unique. I have my own dreams.
My own talents.
You're all little snowflakes, aren't you? Yeah, you're all unique, but frankly, I shove you to the street because your uniqueness isn't all that charming. And I get to it already.
How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business.
Brother, so yeah, you should have done it the right time, right way the first time.
And our special business today is the subject of inertia. And I must make the matter, the idea clear, as follows. Here we have a block of wood at rest on the tabletop. And I ask, what does that block want to do? Answer, the block wishes to remain at rest. Supposing now I have double as much block.
Okay, so let's understand. It doesn't wish anything, it doesn't want anything, it doesn't need anything. It was perfectly fine, it just couldn't give a shit. If you want to do something, then you just got to ask it to do it. You didn't ask it to do anything, so it didn't do anything.
And I try, in turn, to put that system in motion. What do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much.
So there's twice as much to move. So again, it doesn't, this whole idea that it wishes, that it's resisting motion, it's just saying, go ahead, try me. And yes, if I weigh more, you have more stuff to move. So you're going to have to apply more energy. But that's it. That's all it's saying. There's nothing else here. There's just, you have to give it something for it to have something. It's not saying, don't give me anything. It's not saying that.
And therefore we say its inertia is twice as great. And so you discover at once that I have used the term inertia and referred to the idea of mass as synonymous.
There, so for all the retards, that's all it is. It's just mass. You're just saying there's more or less mass. When you say there's more or less inertia, that's it. It's just more or less mass. Period. End of the subject. This is not complicated. There is no magical inertia effect.
So mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do. In English, simply, whatever a body is doing,
That's not what he said, but okay.
that's what it wants to do.
He didn't use this want stuff.
Let's look at Newton's Latin for it.
Good.
Newton put it in Latin. Axiom.
Why? Who can even understand, right? I mean, he's living in England, you know. I mean, what's the point of publishing in Latin? I mean, frankly, it just, you know, you say to yourself, why did they make life more complicated? It just sounds like, it seems like, well, you're only publishing for some elite people that have been trained in this language, and everybody else is out of luck. So it's just some sort of elitist thing. It just has such a taint to it. Why wouldn't you want the book read by everybody?
Mata siva legis motus. Axioms, even laws of motion. Corpus omne perseverare in statu suo quiescendi, and so on. And in English,
Yick.
a little more within our competence.
Thank you. But apparently it's subject to translation. So as much as this Roman Latin language is so well published in, and it's supposed to be a good scientific language, you find lots of different translations. So
Every body continues in its state of rest or of uniform motion in a straight line, unless there are some forces to divert it.
I don't think that's what that said. But clearly it doesn't say anything about wanting, okay? And it doesn't say anything about resisting. It just says that you have to move something to move something. Not a very complex law. You have to give it energy, or it does whatever it's doing. You have to counteract what it's doing, or you have to give it an action. But that's it. There's nothing more complicated.
Consider now the following. Here you come on April Fool's Day, let us say, on a package, on two packages resting on the ground. Here is one and here is another. And you deliver, you impose a force on the one. I will, instead of with my foot, with my hand, and it experienced such a motion. The force produced a motion in the body of so much inertia. Now I try it with this one. Hardly as much motion. Why? This one is filled with rags, and this one with 2 bricks. And this one has the greater inertia.
You could just say, you could put it on a scale and say, yes, it weighs more. And exactly how much it weighs is going to be proportional to how much it resists being moved. Plus, you have to factor in the gravitational resistance.
So, the measure of the mass of a body is its inertia. Consider now the two aspects.
So, do you hear that again? The measure of the mass of a body is its inertia. There. Come on. Just quit pretending inertia is some new important word. It doesn't mean anything.
Aspects of Newton's first law. A body at rest wishes to remain so. Here I have a heavy block of wood, a hole in it, and I put a dowel rod in the hole. The dowel rod constitutes the handle. How can I put that handle into the block? As follows. As follows. Notice what happens. I hit the handle. The block remains at rest.
Well, so we didn't notice it, but yes, he could have put a mark on there and shown it going in or something, you know. So, clearly, you know, yes, he's just suspending it and just hitting it in suspension, and his suspension is flexible, so his grip doesn't stop it from moving, so it does actually move into the block with a higher velocity than the block can go. The block is big, it doesn't want to go the same velocity as the stick. I shouldn't have said want. It won't go the same velocity as the stick because it's got more fish to fuel, so to speak. If it's gasoline and you just thought of the mass as being how much you got to fill the tank, these little tanks fill easily. The big tanks fill hard, so you can't get enough fuel into the big tanks to move fast.
Whereupon the handle moves into the block. That's the first law. The body of large inertia wishes to remain at rest.
So if you made it really hard friction, it won't work. So if there's a lot of friction here, it won't work. It won't work if there's too much friction where his hand is. So you can understand that there's ways to make it not work.
Let me pursue this in another way to demonstrate the second part of Newton's law. What did the second part say? If the body is in uniform motion in a straight line, that's...
So now he's just going to reverse it. And now he's going to put the block on the top and let the block's weight, give it motion through letting it fall in gravity, essentially, or using his own hand motion, and then stopping it. And the thing with the greater weight can't get... it's got more total energy than the stick can absorb, and so the block will move into the stick.
That's what it wants to do. I start again. Now I come down on a firm block. The motion of the handle is arrested. The handle and the block were moving. And what does the block want to do? Keep moving. Whereupon it lodges itself more firmly.
It doesn't want to keep moving, and it's just that this isn't enough to stop the block. The friction isn't enough. The energy can't be communicated to the whole block to say we're going to reverse your direction or stop your motion. So it continues to move because there's not enough counter force being put into the block.
On the handle. Thus do we demonstrate Newton's first law in two parts. Let me do this another way.
The interesting point would be to bang it on a scale or something that could measure how much pressure there is, because the more the block moves, the less pressure the point at the end of the stick is going to feel. So the pressure where the stick hits is completely dependent on how much the block weighs. I mean, how much it moves. If it's allowed to move further down in gravity, then it'll be less pressure on the stick.
Pretty. Very pretty. I have a support and a weight W supported by a string and another string with a loop in it here, which I shall show you. Let me call this string A and this string B. I propose to...
So this is the Professor Lewin experiment. So it's kind of funny that you could go, before you go to college, you could watch these 40 videos and you'd frankly see a bunch of the experiments you're going to see in your, $20,000 a year MIT lecture. Well, now it's 40,000, whatever.
Do as follows.
60.
I'm going to pull on string B, the lower string. And I can break either string B or string A by invoking Newton's first law. If I pull suddenly on string B, W wishes to remain at rest, and B will break.
So this is the wrong way to analyze, and so I'd say the way they're talking is just wrong. The fact is it just takes time. It takes time for it to be, the energy to be communicated through all of these strings. So the string A, when you pull on string B quickly, what you're basically doing is you're telling A never even feels it. Doesn't know you're pulled on it because it happens so fast, and all it's really communicated to is the weight. And so you haven't gotten the energy to this weight even for 2 to recognize that you increased the pressure. So this string breaks because you did it quickly and it never got communicated to the other string. And if you do it slowly, then yes, the weight gets communicated here. The A realizes there's more weight being pushed on it, more force, and so it knows about it. So it's just the elasticity of the string that's really deciding that it's going to take time for this event to take place. So maybe if they used wire instead, because it'd be much quicker to communicate the weight, then string A would always break, no matter how fast you pulled on it. But it's only because they're using a string that stretches that, string A doesn't know that you're increased the weight.
On the other hand, if I pull gently on B, A supports W already there, plus the force I impose. And I shall show you that exactly with this demonstration. Here is a string, here is a hook, here is a weight, and the upper string is supporting the load. Here is the lower
So it's only barely supporting it.
String, and I am putting a little rod inside here so that my hand is not underneath should the weight fall. I am going to break the lower string. Watch it now, the lower one. There it is, I broke it. Now I am going to change the string. I'm going to change the string. And now I am going to break the upper string by pulling slowly on the lower one. Watch it now. Watch. We hope that breaks. Now supposing it does not. One is led to say the experiment has failed.
So he makes this speech more than once about how, these errors are acceptable, but frankly, they really shouldn't be. You should do everything quite clinically and correctly and get the right answers instead of wrong answers. Because we know that in the hands of the malicious, the people who want to cheat, it's very dangerous having these aberrant events take place.
And I say, no, the experiment doesn't fail. I have failed to meet the requirements of nature. Watch, I'm going to break the upper string. There it is. And so we can be applauded for success. Consider another demonstration of the same. Here is an enormous weight, 16 pounds. Here is a string attached to it. If I pull on that string in a gentle way, I'll do it by hand, in a gentle way, The string can support the load. Now let me try to accelerate it. What does Newton's first law say? Body wants to remain at rest. It has enormous inertia. Watch it.
So it's just the fact that you can't convert a very quick velocity into a very large object quickly. And that's the fact of it. It takes time. And so you're not going to be able to move the big object until you have collected quite a bit of energy. And if you're not giving it enough time to collect the energy, it's not going anywhere.
Do you see? The string has broken. I shall have more to say about this when I talk about Newton's second law.
Good.
The second law. Consider now another dramatic demonstration. An application of Newton's first law. Because we must not escape the fact that these laws of physics, of nature, of science, have vast applications in plebeian things. A brick, a trowel. Cannot the craftsman, the bricklayer, utilize Newton's first law in this way? Notice if he hit his hand with the trowel, he'd hurt it. But he can hit the brick with absolute abandon.
Yeah, it's a pointy thing. So yeah, and the brick doesn't get to say ouch, but it felt it. So I don't think that really shows the first law at all. In what way? Frankly, it's really just about, can you stab a brick? No, bricks are hard to stab.
And feel nothing. Inertia of the brick. Here is another classic, which I like to do.
I guess he's saying the brick's motion will dull the amount of motion conveyed because you have to move the whole brick. So if you have something in your hand, it obviously makes your hand less sensitive to pressure. So the heavier the weight you put on your hand, the less sensitive it is to measuring anything's extra weight.
Because it is so dramatic.
I like
a sheet
this
of paper.
This one's a good one. So yeah, this one is really, this is good stuff. This is good physics.
About 20 inches by 30. 20 inches by 30. 600 square inches. The load on each square inch is roughly 15 pounds. Atmospheric pressure at sea level. Therefore, about 9,000 pounds of air on that paper.
So if you tried to lift it in a cubic way, straight up, a meter distance, blah, 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 you can calculate it to be this, a ton of weight on the paper. That's how much air you have to move.
That's enormous inertia. Proof. Here is
It's a mass. So it's a lot of mass, even though we're in it all the time. It's a lot of mass, but the mass is pushing on us from all directions, so it doesn't feel like it.
Board. 1/4 inch thick. I put the board under here. And now I am going to try to put that enormous mass of air into motion by a sudden impulsive blow on this end of the stick.
So he's going to try to move, it's a cylinder, and he's going to try to move this gigantic cube of air above it. Okay, and that's the trick of it. It's not even a cube of air. I mean, technically it's all the air going up has gravity, and it's all being, pushed down on the paper. So it's a huge volume of air that you're pushing.
The impulsive view that people have is, the whole thing will catapult. No, it will not. Because that mass of air is at rest, and Newton said it wishes to remain so.
So it doesn't wish to remain so. It says you can't get to this high velocity into the big giant thing into a slow velocity. It has to do conversion. It has to convert the fast velocity into a slow velocity. And that takes time. And if you don't give it time, it ain't going to happen. But the interesting thing is the paper itself doesn't rip. You would think that there wouldn't be enough, so he has the board, enough board under here where there's enough tension so he doesn't rip the newspaper. So obviously if he had it sticking out further, it wouldn't work because the paper would rip.
Oh, watch it. It did not move. It did not move. Fantastic.
But my hand's broken. Yeah. No. He obviously did the experiment successfully.
Now, remember, ladies and gentlemen and boys and girls, when I refer to this block being at rest, And then I say, what does it want to do? And the answer is it wants to remain at rest. I would not have you dispose of this as trivia, because it took the genius of an Isaac Newton to establish it. Nothing trivial.
Okay, whatever. There's nothing trivial about it, but it's the wrong way to think about it. Okay, so frankly, personally, I'm going to object. Okay, because things should be thought of as being in free space without friction. And, friction is the deceiver, because you have to break friction. Friction is essentially, if something's not moving and it's in an environment that can create friction, you have to think of it as that it's actually sunk in the mud. It's in a deficit. You have to apply more energy to get out of the deficit before you can have just the regular static friction, or the unstatic, the active friction. So before you can have the kinetic friction, you have to get out of the static friction, which is higher by whatever, a few percent. So, it's more complicated than this. Nothing's resisting motion. So if this is in free space, this block, I can hit it with a piece of dust, and it's going to absorb some of the motion because it's not going to be stuck by any kind of friction.
About it. Consider another dramatic demonstration. Oh, this one is a beaut. Here is a vessel of water, and it has quite some inertia, and I put it on this paper,
We've done this too.
and I move it slowly.
Slowly.
Remember,
We
this
saw
has
this in the
large inertia.
short
It
video,
wants to
I think, right? That short video, we saw this same experiment.
remain at rest, and I am not trying to accelerate it too rapidly, and thereby friction forces hold it onto the paper. And so I pull more and more and more.
So you're increasing the contact time, which means there's time for the force you're applying to be translated into the slower velocity that this needs.
And more. We're in a little trouble because friction isn't right for me. But anyone in his right mind must testify to the prospect, if I continue in the manner I have been doing, the whole thing will fall down. But if I invoke the laws of Newton, the first law, which says it wants to remain at rest and will refuse to be moved by short-lived impulsive forces, watch it. Are you not surprised that it stayed there? Consider another.
And it's not because it wanted to. It's because you didn't give it time to. You didn't stay in contact with it long enough for it to absorb any of the energy.
More application. Here is a vehicle, and here is a body standing upright in the vehicle. And now I want to show you that if I move the vehicle, the body is at rest with respect to it. And what does it want to do? It wants to stay there. Watch it. And so it did. And that's why when you accelerate a car rapidly from a standstill, your head is jerked back because of the large inertia of the head. On the other hand, if the car is moving uniformly, if I now suddenly arrest its motion, what will the block do? Well, the block was going straight, and that's what it wants to do. Oh, notice I accelerated too fast the first way. There it is, and the block tipped forward.
Again, just a matter of time.
Quick one for your inquiry. Here I have two vessels, and remember the subject is inertia. They each contain 1 pint.
Oh, yeah.
And let us say that one is filled with cream and the other with milk. So I have a pint of milk and a pint of cream. Quickly, which has the greater inertia?
I don't know. I have to know how dense cream is versus fat versus water. The milk's mostly water. So I guess water is more dense. So let's see what happens.
That's equivalent to asking which has the greater mass. That's equivalent to asking which has the greater weight. And some are led to say, oh, the
fat floats on water, so you can assume, okay, it's less mass.
The cream, of course, because it's thick and sluggish and viscous. Oh, no, mistake. The milk has the greater inertia for reasons, of course, you see clearly yourself. The pint of milk weighs more than the pint of cream. Another demonstration.
So you can see that for ourselves. I don't know how I can see that. So I guess the only way to understand it is that fat cells are less dense than water. So if you replace the fat cell with water, it would weigh more.
Here is a stack of coins. They happen to be Australian pennies. Why? Because they have larger inertia than U.S. pennies. And now what can I do? With a thin blade, I can deliver a sharp, impulsive blow to the lowermost one. And what do I hope to see? I hope to see the whole stack remain unmoved. Why? Because it's at rest and wants to stay. There it is. There it is. There it is. And I just love that demonstration. Why? Because it is a classic revealing the beauty and strength and simplicity, in a sense, of Newton's first law.
Well, it really isn't. It's about friction and, again, about the contact time and blah, blah, blah. And you can't translate the motion to the whole pile because that has to be a slower velocity.
I want to show one more. Remember what the second part of the law said. I would urge you never to forget that the first law has two parts, which are rarely ever properly separated. I said a body moving in a straight line wishes to continue so. Here is a ball swinging in a vertical plane, in a vertical circle. I would remind you that at the instant in question, when the ball is right there on the end of the string, its motion is tangent to the path at that place. And if I should cut the string or let go of it, the ball would not go radially outward, but would go instantaneously in a direction tangent. So, this...
I mean, instantaneously is a tricky word there, because again, it takes time for it to know you let go of the string. But it's a tiny amount of time. But yeah, this is, so again, the idea is you're applying a force, and then you release it from that applied force. So the applied force that's keeping it in this orbit. And so now it's just, all that's left is the velocity it has, and it just goes in a straight line.
This introduces here, in a passing way, the idea of centrifugal force, which is a nasty thing to handle, and often much is said that is wrong. But if I let go of the string at the top, where will the ball go? Tangent. Watch it.
There's just a velocity. So all you have is a velocity. It doesn't matter whether it's angular, circular, or any other motion direction. It just matters that it's moving in a direction, period.
There it is, tangent. Now, it is proper, before we conclude a program on Isaac Newton, to show you one of many photographs of Newton.
These aren't photographs, right? I mean, they didn't have photographs till like the 1800s, right? So, can't be a photograph, I don't think. Must be a painting.
A very important place this man occupies in the history of humankind. And I would hope that when you go to London sometime, you will most certainly go to Westminster Abbey and see where he is buried. And what does it say on that beautiful epitaph? Among other things, let men rejoice that so great a one has existed. So we are coming shortly to the end of the program. One final enchanting thing, an array of cups. If I put this heavy block on them gently, I can drive this spike into that block without the cups feeling anything. Why? Why? Because the block has enormous inertia. If, on the other hand, I drop it, it's going and it wants to keep going. There it is.
Obviously,
and thus I conclude, ladies and gentlemen, a program on inertia. And I thank you for your attention.
But the cups didn't break that dramatically, right? Only a couple of them did and went sideways. But anyway, yeah, close enough. All right. So we'll give you 15 minutes or so of chat time, and then I'll call it a video. Let's see. I need this one. No, I need this one. Nothing. I mean, woof. Anyway, it would be interesting to see you go over some videos on electromagnetism. See, well, the trick is that there's, it's more complicated, and so there's pieces you can agree with, and there's pieces that are just absolute crap. But it gets complicated because it is creating, electromagnetism is induction, okay? So the magnetism part is an inductive aspect. You're creating a magnetic field, and to create the magnetic field, obviously that's something it has to come from somewhere, and the point is it's a reflected field. But anyway, and communicate with your agreements, disagreements, etc. Thermodynamics also. Well, anyway, I have done it in previous videos, so it's not like I haven't done that. I guess I'm just arguing that I haven't got it perfect yet. You know, in the sense that I know it's just the shape of the atom, so you're just polarizing the atom, you're squeezing the atoms, essentially. That's what the electricity is doing. It's just squeezing atoms and then letting atoms release and squeeze and release. And so an atom gets squoze. It's next to another atom. It shares what it got squozed, and they both become squozed by a little bit less. And then that one's connected to another atom, and it squeezes in a little bit less. And so it just keeps... They keep trying to share the same pressure. So each atom you pressurize is connected to other atoms that are going to take that pressure. So it's the taking of the pressure that is the movement of the electricity. And obviously it depends on whether you have high pressure going through a few atoms or you have a medium pressure going through a lot of atoms, and that's the difference between voltage and amperage. Anyway, this guy is certainly an interesting character. I need to watch the rest of his videos. Yeah, they're all worth watching, but I guess I'm just saying, but obviously some of it I don't like what he's saying, right? I mean, the whole idea that this inertia thing, that masses say I am resisting motion, when masses aren't saying that. They're just saying that I can only move if you give me the energy in a form I can eat. They can't take the energy in any form. You have to give them money they can use. You have to give them the right kind of currency. I think is a much better way of explaining it. I mean, if one fish is going 50 miles an hour and it bangs into 50 fish, you understand the idea is the 50 fish can't go 50 miles an hour. Okay, the 50 fish have to go 0.5 miles an hour. I probably said that wrong, 0.25 miles an hour, something like that. I should try to use examples that are more reliable than relying on my memory. But, yeah, it's all work. Let's see if anybody's got anything else. I just get the hell out of here. See if there's anything happening. See how many people there is. 10. We lost 5. That's pretty bad. Yeah. Wow. Okay. Well, that's the way it goes. It's a tough audience. Blah, blah, blah. So, let's see what else we can do here. I'm a bit tired. Let's see. I need to watch. Okay, you had 17 today at one point. Yes, well, whatever. Of no value. Yeah, 17 still isn't enough. Oh, you can hear the outside. Interesting. I have the camera on. I'll have to turn the volume off there. Monitoring my environment. Anyway. Alright. Just 2-minute warning kind of thing. Let's see, is the conduction and insulation of heat related to conduction and insulation of electricity? Well, I have to think for a moment. Obviously, you can't insulate against, say, the magnetic field. It's really hard to create an insulator against the magnetic field, so that doesn't really work. Insulation is really just preventing contact, right? So it's contact insulation. It doesn't really change the wire any. So if I have transmission lines and I put insulators on the wire, rubber insulators, it's not going to change the fact that the transmission lines are going to interfere with each other if they're in proximity because of the field effects they're creating. So in some ways, I don't know if it's a really good analogy. The best heat insulator is a vacuum, because the atoms can't communicate with each other. Right? So, I mean, and all you have is the radiant heat. I mean, the photons can still go through the vacuum. But I guess it shows how little heat is in the form of photons. So let's see how else to explain that. I mean, that's sort of the interesting one, right? Because you're really making something non-reflective by creating the vacuum. You're basically preventing energy from... No, you're not preventing energy from bouncing off the interior. But there's the two layers of glass, I guess, that essentially already absorb the photons and readmit them at their temperature. So that's the problem. The first layer of glass, let's say if you're using glass to insulate, to create the vacuum in between, the layer of glass is going to disrupt all the radiant heat in the form of radiation or photons. So you can only get the temperature of the outside layer of glass, because none of the photons can reach the second layer of glass. Yeah, that's the trick. Get a green screen. Why should I bother? So you can add animations behind you. Yeah, if you people are if my audience is that desperate for entertainment or whatever you want to call that, I mean, if you need that, then you can't really do physics, because physics isn't about that. That's a cartoon. Okay, that's a TV show or something. I mean, you're not really taking understanding and thinking very seriously. I mean, I just want to make my arguments and have the counter arguments made and get to a resolution. I'm not really doing this for the theater aspect. Okay, this isn't a play, or I'm not dramatizing something. I'm not I'm not here to entertain. I'm here to make an argument. I mean, it's like saying lawyers should use green screens, and that lawyers should, no, they shouldn't. They shouldn't, put a wig on and do theater. They should make arguments. Okay, that would be a distraction to I don't know if it's a distraction, frankly. If you do it well, it's probably an enhancement, but it's just shouldn't be anywhere close to necessary for people who give a shit about the subject. And that's all I'm really interested in conversing with, are people who give a shit about the truth. So, the script is more important, I suppose. And obviously I don't write the script, which is probably... some of that I should do to make sure I say things accurately and the way I wish them to be conveyed and all that kind of crap. So, I mean, that would be a more important enhancement of my videos, is that I do a little more work before I make the video. But, I don't think it needs a green screen. It's a huge disadvantage. I have blonde hair, so green screens don't really work. You have to use blue and some other colors, because the blonde hair just doesn't really green screen well at all. You have to have perfect lighting. And a lot of, it's not as simple as you just put a green screen behind you and everything's fine. It's a lot more complicated than that. I used to do it, the cheap version of it as a joke, when I did my gnoozes, and it was pretty funny. It's a more familiar look, so I mean, people do like that just because it looks like professional, But that's all. It's superficial. It's beneath my dignity to resort to, I could wear a Barney the dinosaur suit, and I could do a lot of things to make the videos more broadly entertaining, but is that really what do I have to do that? I have to seduce the audience with, lead paint? Let's see, you should write down questions. Yes, I, of course, should do your job for you. So, yes. I already do that to some extent. I mean, I have, repeatedly said things and just trying to drive home points. I mean, stuff that should really leave a pause in your brain and say, gee, how can that really be true? I mean, how can it take 4 times the fuel to go twice as fast in all circumstances? Their physics says it takes twice the, 4 times the energy to make this thing go twice as fast. That's what their physics says, and they don't have a single experiment showing it to be true. I mean, it's such a glaring deficit, and you're just like, I almost shouldn't have to argue much past that, except to say, okay, there is really no evidence of this thing, so why are we bothering talking about it? Let's agree that, yes, momentum works, and this other crap doesn't help at all. The only way to get an audience attention today is brain-rotting entertainment. I don't think it's the only way, so again, I don't agree with that statement at all, but whatever. I don't have the same opinion as you. I mean, obviously popularity just has to do with exposure. And the more you're exposed to something, the easier it is for you to get addicted or, to be interested. And that's all it really takes. Is you don't have to, look, you watch a few of these Julius Sumner videos and you say, well, let's see what else he says. Let's see what else he does. Yeah, so that's all it really takes. And the internet isn't created to create that opportunity for exposure anymore because it's so unbalanced. The popular are so... It's like the rich owning, 1,000,000 times more. The top 1% owns, whatever, many times more of the world than the rest of the people combined. It's, that's the problem. And the popular don't do anything to broaden, to show the audience something else. It's just like YouTube's giving you a warning. Are you sure you want to leave our website? They don't even let you just leave. They have to let you know that you're leaving their valuable website. They have to put some deterrent in the way to stop you from leaving. And obviously the popular don't do anything that might distract from their own audience. It also doesn't help that YouTube blacklists channels. Well, whatever. It's not the blacklist that's the problem. It's the whitelist that's the problem. Their favoritism is the glaring giant problem. They make the popular more popular. They don't do any of the find the gold thing. So anyway, you people really are off the subject. So, I think we'll call it a video and such. So, till the next time. Blah, 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 blah. Just consider all those wonderful things I said to you personally. Blah, blah means, oh yes, you're so charming. You look marvelous. Some kind of crap like that. Yeah, just pretend.